students, let us start our discussion about mutual inductance. So for this we have to take two different coils. Let us take the first coil, which can be represented by a particular symbol S1, because this coil forms a particular solenoid. So we take S1, that is solenoid 1, and another coil which has a larger radius in comparison to the first one. So this can be represented by symbol S2. Let us take the radius of the first coil for S1. If the radius is equal to R1 and then cross section area, this becomes pi R1 square, and number of turn per unit length, so you can write it as number of turn per unit length. It can be taken as N1, okay, and length of the coil is L. Length of the coil is L. So if we represent the N1 as the total number of turn, then N1 will be equal to N1L. Here this N1 is the total number of turn present in the inner coil. Okay. Similarly for S2, if its radius is R2 and cross section area is pi R2 square, and number of turn per unit length is equal to N2, and the length of the solenoid is also equal to L. Length of the coil is equal to L. Then total number of turn in this coil will be equal to N2. So this N2 equal to N2L. This is the basic physical condition related to these coils. Suppose that if we maintain a particular current I1 through the inner coil, then what will happen? As we connect a particular current I1 through the inner coil, then there is a magnetic field created inside the first coil. So the area of the first coil in which the magnetic field is generated, so this can be represented by a particular value B1. So case 1, when I1 is set up in coil 1, in S1, okay, so the magnetic field inside the coil is equal to mu 0 N1 I1, mu 0 N1 I1. Now what will be the value of the flux linkage to the second coil? So as we know that in the simple case of the mutual inductance, the flux linkage to the second coil due to the current flowing in the first coil phi 2. This is the linkage flux in the second coil. So if the number of turn is N2, then the total flux linkage will be equal to N2 phi 2. This N2 phi 2 is directly proportional to the current flowing through the first coil. It means this can be written as I1, and here is a constant that is known as M of 2. This is the mutual inductance of the second coil with respect to the current flowing in first coil. Okay, so this is the equation number 1. So if you want to calculate what will be the value of this linkage flux N2 phi 2 in the second coil. Then if you want to calculate this, then what will be the value of this N2 phi 2? From here N2 is equal to N2L, and this phi 2 means the flux linkage to the second coil, and we are seeing that the area of the second coil is larger than that of area of the first coil. And we well know, if there is a current flowing through the inner coil, then there is a magnetic field only inside the area of the first coil. It means the outside of the outside area of the first coil, the magnetic field is 0. It means the magnetic flux linkage to second coil will occur only inside the area nearly equal to the area of first coil. Okay, so magnetic field is B1, the magnetic field inside this coil, that by which the flux is linkage, this is B1, and also the area of the first coil, because in this area the flux linkage and the remaining area of the S2 is not affected by the magnetic field, so the linked flux will be written by this formula. Okay, so this is equal to, if we write the value of this B1, then we get N2L into mu 0 N1 I1 into A1. A1 means pi R1 square. So from here we get a formula for N2 phi 2. This is equal to mu 0 N1 N2 and L dot pi R1 square dot I1. This is equation number 2. From equation 1 and 2, we are seeing that the LHS of both terms are same. Also, the RHS term contains the coefficient of I1. The coefficient of I1 in first is M21, and the coefficient of I1 in second equation is mu 0 N1 into L pi R1 square. So on comparing equation 1 and 2, we get M of 2 1. It means the mutual inductance of the second coil with respect to the current flowing in the first coil, or due to the current flowing in the first coil, is equal to mu 0 N1 N2 L dot pi R1 square. But here we can say that this mutual inductance does not depend on the current flowing through the coil, because in this term there is no any term of the current. So we can say that the mutual inductance is free from the current flowing through the coil, but only it depends on the geometrical conditions of the both coil. It means number of turn per unit length of both coil, length of the coil, and the cross sectional area of the inner coil. Okay, so this is a particular formula for the mutual inductance of the second coil. Now let us calculate the second case in which there is a current flowing through the second coil, and want to calculate what will be the flux linkage to the inner coil. Okay, so let us start our discussion for the case 2. When I2 is set up in S2, then what will happen? And you can write this equation as equation number 3. Now when current I2 is settled across the second coil, then the magnetic field inside the second coil can be represented by a particular term B2. This B2 can be expressed as the magnetic field inside the solenoid. This is equal to mu 0 N2 I2. If we leave the edge effect, then this equation will occur. Now as we want to calculate what will be the value of the flux linkage to the inner coil, it means if you want to calculate what will be the value of N1 phi 1, then we can write it as the total flux linkage to the inner coil will be given by, or this flux linkage will be given by in terms of the current flowing in the second coil, that is I2, and there is a constant that is known as total flux linkage to the first coil. So the mutual inductance of first coil, it means inner coil, with respect to the second, this is M21. So if we take this equation as equation number 4, then now if we want to calculate what will be the value of N151, then we can calculate it as easily. What is the value of N1? From here N1 equal to N1L, and phi 1, so phi 1, what will be the value of this phi 1 across the first coil? So phi 1 means the total magnetic field inside the first coil, and the magnetic field inside the first coil is B2, and the cross section area of the first coil, that is A1. Okay, so if we put the value of this B2 from here, then we get mu 0 N2 I2 and area, that is pi r1 square. So from here, after rearranging, we get N1 pi 1 is equal to mu 0 N1 N2 L dot pi r1 square dot I2. Okay, so if we put this as equation number 5, then on comparing the equation number 4 and 5, the LHS of both equation is same, and in right term here the coefficient of I2 is M12 and the coefficient of I2 is mu 0 N1 N2 L pi r1 square. So on comparing 4 and 5, we get M12 is equal to mu 0 N1 N2 L pi r1 square. This is equation number 6. You are seeing that from equation number 3rd and equation number 6, M21 and M12 both are same. So we can say that if the total length of the both coil is same and one coil is totally covered the second coil, then the mutual inductance of such type of both coil is always same, and they are given by the formula mu 0 N1 N2 L dot pi r1 square, where pi r1 square is the cross sectional area of the inner coil, and L is the length of the both coil, N1 is the number of turn in the first coil, N2 is the number of turn per unit length in the second coil, and mu 0 is the constant, it is known as permeability of the free space. Okay, so this is a basic concept. From here, from equation 3 and 6, we can find out M21 is equal to M12, so it can be written as M. So this M can be assumed as the mutual inductance one of the two coil, mutual inductance of one of the two coil. So the formula for the mutual inductance will obtained as M equal to mu 0 N1 N2 L dot pi r1 square. With the help of this formula, we can solve different types of numerical problems given in your textbook. So solve these problems. Okay, till now, take care. Thank you.